Okay, so let us start the algorithm. So it's called the Kruskal's algorithm. It's kind of very simple to understand. So let us use this example to understand the working of it. So given a graph with edge weights, your first step is to sort all the edge weights. So you know several sorting algorithms by now. So you can sort all the edge weights. So if you, that will be like n log n at the best case, right? So you can use an n log n algorithm and sort all the edge weights if you have the edge weights given to you. All right. So assuming you have sorted the edge weights, now we go through a sequence of iterations. So initially each vertex is what is called its own cluster. You can also call it as a component. So let us use the term component. That is kind of more regular standard for this algorithm. So we consider each vertex to be in its own component. Okay. So now you can also identify the components using a component ID. So the standard is, to begin with, in initialization, each component is identified with the ID of the vertex itself that is part of the component. So the component ID is indicated in the red color on the top, and inside the circle have the vertex ID. So S, W, X, U, V, Y in black are the vertex IDs, and the ones in the red on the top are the component IDs. So S is in component S, W is in component W, X is in component X, and so on. So that's the initialization. So now we are going to go through a sequence of iteration. So in each iteration, we are going to pick the next possible smallest edge weight that we can consider and incorporate that edge here, so that we are bringing two components together. So each component or a cluster, as I said before, is a minimum spanning tree by itself. So to begin with, each vertex is its own minimum spanning tree by itself. So now we are going to connect two components using an edge that is the smallest possible weight, so that you are basically bringing two minimum spanning trees together and making them as one minimum spanning tree. And essentially by that process you are reducing the number of components by one. So we have 6 components here. Now for the first iteration you pick the smallest edge weight, which is 1. Now if there's a tie, you can break the tie in any order. So let us say we pick this edge of weight 1. So now you see here, when you, before you incorporate that edge, make sure the end vertices of that edge are in two different components. So the end vertices of that edge here are X and Y. So X is in component X, Y is in component Y. So if, since the end vertices are in two different components, it is okay to incorporate this edge and make the two components to merge as one component. Okay, so why I say that we need to make sure the two vertices should be, the two end vertices should be in a different component. We'll later come across some scenarios dealing with that, but let me show you an example right away why it should be taken like that. So let us say this is our set of spanning trees. So this is now one spanning tree, and this G is on its own component. Now if I were to pick the next largest, next smallest edge weight, let us say it comes out to be the edge between B and C. Okay. Now the edge between B and C, B and C are already in the same component because they are already part of one minimum spanning tree. So if I add this edge BC, it's going to only create a cycle. Okay, because both B and C are already part of the same component. So if I add one more edge in this component, it's going to create a cycle. So we want to make sure each component is a tree, not having any cycle. Okay, so that's why when you are going to add an edge, a new edge, you have to make sure the end vertices of the two edges are in a different component. Okay, right. So X and Y are in two different components. So when you merge them, they belong to one component. Now when you are coding this algorithm, you have to also make sure how you change the component IDs. So before you merge them, they are in two different component IDs. So after the merger, we'll pick the smallest of the two component IDs, which is smallest of X and Y. Alphabetically it is X. So we say both the vertices are now in component X. Okay, so that's all. These are the coding details you have to take care of. Alright, so this is the kind of set of components we have at the end of the first iteration. So we'll just continue the same process. So now pick the next smallest edge weight, which could be this one. So this one is between W and V, and W is in component W, V is in component V. So we could merge the two components using that edge. So add that edge. So, and also the component IDs, V is smaller than W alphabetically. So we will make both W and V to belong to component V. So as you see now, from 6 components we are reduced to 5 components in this iteration. Now we have only 4 components. So now continue the iterations. The next smallest edge weight is 2, and this 2 is between U and V. U is in component U, V is in component V. So it is okay to merge the two components. Again, you see, when you're merging, you're basically merging two spanning trees. This is one spanning tree merged with another spanning tree. So this becomes now one single component. And for component ID, we take the minimum of U and V, which is U. So all the 3 vertices U, V, W are now in component U. Okay, so now continue the iteration. So pick the next smallest edge weight, which could be 3. I could pick this 3. Again, as I said, you could break the tie in any order. So let us pick this 3 between V and Y. V is in component U, Y is in component X. So there are 2 different components. So you could merge them and make them to be part of one component. So you take the smaller of the 2 component IDs, which is U. So make all the 5 vertices. Of course, you have to change only for the other component X and Y. So make them to belong to component U. So now all these 5 vertices are part of one component, which is a minimum spanning tree involving these 5 vertices. So now the next smallest edge weight is 3, and it is between S and W. So yes, so this will bring S inside this component. So S is in component S, W is in component U. So it's okay to merge them. So now S is part of this component. So S is smaller than U. So just for completion, all the vertices are now in component S. So now we have all the vertices in one single component, and that is the end of the algorithm. Okay. So this is now a minimum spanning tree, and the sum of the edge weights is 10. So the time complexity of this algorithm is mainly the sorting, is mainly driven by the sorting step. So given the edge weights, you have to first sort them. So if we have E edges, the time complexity to sort is E log E. And then you have to go through each iteration, and each iteration takes like it depends on how you store the sorted edge weights. If you store them as in an array or a heap, you have to spend log e time to remove the smallest edge weight from the main heap and so on. So each iteration will not take more than e log e time, or sorry, all the iterations put together will not take e log e time. So the overall time complexity is e log e. So that's something you have to know as an end result. Okay. So the Kruskal's algorithm is e log e time complexity. So let me see. Any questions so far? You can type. Okay, so can explain iteration 3. So iteration 3, so at the end of iteration 2 we have something like this. So now we have to pick the next smallest edge weight, which is 2 in the graph. So now this 2 is between vertices U and V, and in the previous iteration, or end of the previous iteration, U is in component U, V is in component V. So now you can merge them because the end vertices are in 2 different components. Okay, so now when you merge them, you have to also change the component ID. Say take the minimum of U and V. So that is U, so that way we have to change the component ID of the other 2 vertices W and V. So all the 3 vertices are in component U. Okay, alright, good. So let us quickly go through one more example and then look at some properties and theorem proving. Right, so this is another graph with edge weights. So again you have to get it sorted, And so initialization, each vertex is its own component. A is in component A, B is in component B, and so on. So pick the edge with the smallest edge weight, which is phi. So we could again break the tie in any order. So let us say I pick this phi between A and D. So A and D are in two different components, so it's okay to merge them and make them as one component. And again, A is the smaller of the two component IDs, so D gets component ID A. So now pick the next smallest edge weight, which is this phi. So again, it's between two different components, C and E. So you could merge them, and C is a smaller component ID, so you make E to belong to component ID C now. Now the next smallest edge weight is 6, that's between D and F. D is in component A, F is in component F, so you can merge them and make them as one single component, and F now gets a component ID A. Then go back to the graph. The next smallest edge weight is 7. You could pick this 7 or this 7. I think I pick up A, B. So A is in component A, B is in component B, so you could merge them. So B now becomes part of component A, the smaller of the two component IDs. So then you could really pick this 7 between B and E, because B is in component A, E is in component C. So you could merge the two components with this edge. So as you can see, these four vertices are a part of a minimum spanning tree. The CE, this is the best way to connect them. So now we are connecting them using a smallest edge weight. So there are several edges crossing the two components, 7, 8, and then what else? This 15, 8, and 11. So these 5 edges are crossing or connecting the two components. So we are picking the smallest edge weights, and the algorithm automatically guarantees when it picks the smallest of the edge weights in the sorted order, it will make sure that it is using the small edge with the smallest weight connecting the two components. So this BE is the smallest edge weight connecting the components involving these 4 vertices and these 2 vertices. So now all these 6 vertices are part of component A. So now G is the only vertex that is alone on its own component. So now you see the next smallest edge weight is 8. But if I use this edge of weight 8 to connect B and C are already in the same component A. So if you connect them, it's going to only create a cycle. Okay, so we should not use an edge that is already between vertices in the same component. So if you pick some other edge, say the next largest weight is 8. Again, this 8 is between E and F, and E and F are already in the same component, so you should not connect them with using that edge. Then the next largest weight is 9. If you pick this 9, it's between B and D, and B and D are already the same component, so you should not connect them. So you should keep on doing like checking, finding the next largest weight that can really bring together two different components. So the next edge is 9 here between E and G, and yes, so E is in component A, G is in component G, so you can include that edge and bring G to this component. So now G is part of the minimum spanning tree involving all these vertices. Okay, and the component ID of G is A. So sum of all these edge weights is 39. So it means that's the minimum possible edge weight that you can have for a spanning tree covering all these 7 vertices. Whatever you try, you cannot find a spanning tree of weight less than 39 for this graph. So that's what the minimum spanning tree means. So now next what we are going to prove is the correctness of this algorithm. Okay, so I'll take a second to store this video. You can type any